Hello, I'm Dr. Darren Simmons, and in this video I am going to go through an example of how you can complete most of the second part, or the first half of the second stage of the project for Math 2110, Principles of Statistics. So the goal of this part of the project is to allow you guys to make use of the central limit theorem in the context of the data that you've collected at stage one. So as you can see here up on the left-hand side of the Excel spreadsheet here, I have included the raw data that I used in my video for stage one, and I'm going to be doing some manipulations and calculations with it here in this video. So the first thing that I'm going to need to do is to take some space here and calculate the population mean and population standard deviation for the rolls of the dice here, or the simulated rolls of the dice here. So I'm going to do this here in column D, population mean. And then this is just the formula in Excel, or the function in Excel that calculates means is average. And I need to tell it where I want to calculate the average. In my case, that runs from cell B2 all the way down to cell B61. As you can see here, if you paste down here and then hit enter, and it spits out that the population mean was 3.383 repeating. I also need the population standard deviation, which I'm going to have to abbreviate some stuff here just to make it fit in the cell. For this, the function is called stdev period p rather than stdev period s, which was the sample standard deviation. And we'll be calculating that here. Also, cell B2 through cell B61. B61 there. And you can see that the population standard deviation here was about 1.88844 and change. Now, I am going to format the cells here as I did before, because this is supposed to be a table. I'm going to do this by including the slightly thicker border and outer border and inner border. And I'm also going to put background colors on both of these names here. We'll go with yellow and orange. Obviously, that's not required. The colors are, you could use whatever color you want. I also need to rename this this particular tab because we're going to be making more of them. This one this one's supposed to be labeled raw data, so we'll call it that. Now, that's the first tab. It looks an awful lot like the first tab of the first stage of the project, but we need more. The next tab we're going to be making is going to be a tab where we're going to construct or calculate some direct probabilities. These are going to be calculated empirically. These are actually going to be empirical probabilities calculated with the data on the raw data slide. So a little housekeeping bit here. I prefer Times New Roman font, 12 point, and everything centered. I'm also going to stretch out these cells quite a bit here because I'm going to have to write some stuff out here that's not going to fit in them nicely. Now, specifically, the probabilities that we are going to calculate are the probability that that a die roll is at least 4, and then the probability that a die roll, probability that a die roll is at most 3. Those are the two things we're going to need to calculate. And as I said, these are going to be calculated as empirical probabilities using the data set that we have on the raw data slide. So to do these, we're going to need to count the number of rolls that were 4 or more, and then divide it by the total number of rolls. In my case, the total number of rolls was 60. So I'll need to use the Countif function repeatedly here. So start with equals, and I'm going to need to open a parenthesis because I'm going to be adding up a bunch of stuff here. So first off, Countif you'll see that it asks you for a range and then a criterion. The range is going to have to reference the data that's on the raw data slide. So remember, the way that you get that is either by clicking on it and then highlighting the data, or by typing a single quote, raw data, the name of the sheet that you want to reference, exclamation mark, and then the cells in question. So B2 through B61, that's where my roles are, comma. The criterion I want here is 4. To that, I'm going to have to add some stuff. So that's the number of 4s that I got. I also need to add up the number of 5s and 6s that I got. So count if, again, it's on the raw data, data sheet. So that's raw data in single quotes, the name of the sheet in single quotes, followed by an exclamation mark, and then the cells, which are B2 through B61 in my case, and then the criterion 5. So that will count the number of 5s. To that, I only need to add the number of 6s, and that will be count if, single quote, raw data. Again, that's the name of the slide, the tab that it's on, exclamation mark, B2 through B61, and 6. So those are the ways that we can get a roll of the die that is at least 4. So I need to close my original parenthesis now, and then so that I'm adding these 3 numbers up, and then I need to divide it by the total number of rolls, which was 60. I hit enter. That works out to be 1/2. It just happened to work out that way. If you don't get 1/2 here, that's fine. We'll have to do the same thing here for the probability that the die roll is at most 3. So that's either 3 or less, 3 or 2 or 1. So I need to count the number of 3s, the number of 2s, the number of 1s. So count if, and again, it's going to reference the raw data sheet by putting raw data, the name of the sheet, in single quotes followed by an exclamation mark. The range that the data sits in is B2 to B61 in my case. And then the criterion I want is 3. So that'll count the number of 3s. To that, I will need to add the number of 2s. So count if raw data, exclamation mark, B2 through B61. Whoops, 61. There we go. 2. And then I also need to count the number of 1s. So that would be count if, referencing the raw data sheet. And on that sheet, B2 through B61 are where my rolls are. And lastly, 1 for the value that I want it to count, the number of 1s. So what I've got now, closing that parenthesis, that second parenthesis, is a count of the total number of rolls that were 3 or 2 or 1, 3 or less. So I need to divide that by 60 and then hit enter, and you see that that also works out to be 1/2. Now I'm also going to format the cells to make this look a little bit more like a table, and that means thick outer border, thinner but thicker than they currently are inner border, and I'm going to colorize the background of both of these probabilities. Let's go with green and blue. And let's make the text on that latter, on both of those, white so that it's a little bit easier to read. Okay, so there are 3 more tabs that we're going to need to create here. The next one is where the first one where we're going to be making applications of the central limit theorem and how we can use it to calculate probabilities here. So the first one is going to be central limit theorem with n equal to 30. And again, the same sort of housekeeping bit here that I like to do with the making everything times New Roman 12 point and everything centered. So here we are going to need to calculate, well, first off the mean of the sampling distribution. Sample means. And so we'll see how much wider I'm going to need to make this. Let's just make it 400, and that's still not big enough. Okay, let's make it 500. There we go. And for that, we're going to need to take the central limit theorem into account. And remember, our size of our sample is 30. That's the minimum size for which the central limit theorem applies, regardless of what the original distribution happened to be. So the central limit theorem says that the mean of the sampling distribution of sample means is the same as the original population mean. So this we can get actually by referencing something that we have right here. We already calculated that population mean. So we can get that by hitting equals and then clicking on the raw data bit and then pulling up the population mean here and then pressing enter. So the mean of the sampling distribution of sample means will be the same as the original population mean. Second thing we need is the standard error of the mean. And for that, we're going to need to take into account the formula for the standard error of the mean, which is the original population standard deviation divided by the square root of the sample size. So this will be the population standard deviation from the raw data sheet. And then you'll see I have to go back up to this formula bar here because that's not all there is to it. Divided by square root of the sample size. The sample size here is 30. So what we wind up with here is raw equals raw data d4 over the square root of 30. Hit enter, and we see that the standard error of the mean in this case is about 0.3368. So again, I am going to mess with the cells a little bit to make it look a little bit more like a table with thicker outer borders and thinner but somewhat thick inner borders. And we will colorize these. Let's go navy blue with white text and purple with white text. All right, so that is the mean of the sampling distribution and the standard deviation of the sampling distribution, the mean and the standard error of the mean. The next thing we will need to do are calculate for probabilities. First, the probability that if we take a sample of size 30, its mean will be at least 4. The second will be the probability that if we take a sample of size 30, its mean will be at most 3.5. The third will be that the probability that if we take a sample of size 30, its mean will differ from the population mean by more than 1. And lastly, the probability that if we take a sample of size 30, its mean will differ from the population mean by at most 0.75. Okay, so let's do that over here. So probability that sample mean is at least 4. For this, we are going to need to make use of a new function in Excel that we haven't mentioned yet. I'm going to stretch this out to 300 and see if it fits. Barely. Let's make it 350 so that it fits a little bit better. The function is one that allows us to compute stuff using normal distributions. And it's called norm.dist. In this particular case, though, we want the probability that the sample mean is at least 4. So to get that, we're going to actually have to cheat a little bit. See, the norm dist function only computes areas to the left. So we have to cheat a little bit to get an area to the right, because that's what we need here. We want the area to the right of 4. So what we'll have to do is hit 1 minus first off. And then the name of the function is norm.dist. And you'll see that it has it has 4 arguments here. It asks you for x, that's the bound that you want to use. Mean, that's mu, which in this case will be mu x bar. Standard dev, which is the standard deviation. In this case, that will be the standard error of the mean. And cumulative, which will always be set to true, so that it's computing areas to the left rather than other stuff. So this function will give you the area to the left under the normal distribution curve with mean, whatever you tell it the mean should be, and standard deviation, whatever you tell it the standard deviation to be, to the left of x, which is why I had to do this 1 minus, so that we wound up with the area to the right. Okay, so the x in question is 4, because we want the probability that the sample mean is at least 4. The mean is the mean of the sampling distribution of sample means, which is in A2 here. The standard deviation is the standard error of the mean, which is in A4 here. And then we will need to set the last argument cumulative to true. And so if we hit that, we get our probability that it is about 0.0336 when rounded to 4 decimal places. Excuse me. So the next thing we want is the probability that the sample mean is at most 3.5. And for that, we can use the normal Dist function again, or norm Dist function again. So this is equal to norm.dist of x 3.5, that's the bound. Mean is going to be the mean of the sampling distribution of sample means. That's in cell A2. Standard dev is the standard error of the mean. That's in cell A4. That's why we calculated it. And the last argument will, throughout all of this, be set to true every single time. So we hit enter, and we get that the probability that the sample mean is at most 3.5 is about 0.36355 when rounded to 4 decimal places. So next is the probability that sorry, it doesn't want to cooperate with me. Probability that the sample mean differs from population mean by more than one. So now I'm going to have to widen this quite a bit more. Let's take it out to 500 and see if that's enough. It is not. Let's take it to 550. That's probably enough. Okay, so if the sample mean differs from the population mean by more than 1, then we're in the case where we have 2 bounds. Sample mean -1, population mean -1, population mean +1, and we want the area in the tails. Since the norm Dist function only computes areas to the left, we have to split this up into 2 bits here. So for the lower bound, we want the area to the left. So that will be norm.dist of 1 minus, or excuse me, the population mean -1. That's the lower of the 2 bits here. The mean we want is what's in A2. The standard deviation is in A4, and the fourth argument will always be set to true. To this, we will need to add 1 minus the area to the left of the upper bound, because that's the only way we can get the area to the right. 1 minus, or that is a way that we can get the area to the right. 1 minus norm.dist of A2 plus 1 with mean A2, standard deviation A4, and the last argument set to true. And now I close all of my parentheses and then hit enter, and we get that this probability is about 0.0030 when rounded to 4 decimal places. Lastly, we need the probability that the sample mean differs from the population mean by less than, or excuse me, by at most 0.75. And for this, we are going to, that's the same case where we have 2 separate bounds and we want the area in between them. So here's population mean plus 0.75, here's population mean minus 0.75. We want the area in the middle. And again, since the norm Dist function computes areas to the left only, we're going to have to take the big bound, norm dist of the big bound, et cetera, et cetera, et cetera, minus norm dist of the small bound, et cetera, et cetera, like so. So norm.dist of x will be the mean plus 0.75. This is our upper bound here. The mean is A2 in A2. The standard deviation is the standard error of the mean in A4, and it will be set. The cumulative should be set to true. From this, we have to subtract the area to the left of the smaller mean, so that we get everything to the left of here that's not to the left of here. So what's in between? So that's norm.dist of the population mean minus 0.75. The mean is again the population, the mean of the sampling distribution. The standard error is again the standard deviation, excuse me, is the standard error of the mean, and cumulative will always be set to true for our purposes here. So overall, what we wind up with is norm dist of A2 plus 0.75, A2, A4 true, minus norm dist of A2 minus 0.75, A2, A4 true. And we hit enter, we get that that probability in question is about 0.9740 when rounded to 4 decimal places. All right, so again, I'm going to play around a little bit with the cells so as to make it look more like a table. Same bits as before, thicker borders, and I'm going to colorize each of these bits here. So let's start with red, and I think white text would be a little bit easily readable. Then orange, black text looks fine. Yellow, and then green, and white I think will show up a little bit better there. So that's all we need for this tab. The next tab is going to be a little bit different, and it's going to be central limit theorem with n equal to 45. I'm going to leave it for you guys to do this one yourself. You're going to repeat all of the things that I did in the central limit theorem n equals 30 slide, except replace 30 by 45. Lastly, we have the fifth tab, excuse me, which is summary. And here you're going to need to throw in a text box. So that you hit insert here and click on text and text box. We're going to drop it from upper left down to here, say, about there. And then in here, we will need to set the text, or the font. It's definitely supposed to be Times New Roman 12 point. And then you will need to write your summary here. So it should be between 3 and 5, from 3 to 5 paragraphs of text with the describing what you did, what your calculations were, the outcome of your calculations, comparing some stuff together. Go ahead and have a look at the assignment sheet to be sure exactly what it is you're supposed to discuss here. If you have any questions that you would like to address about this that I didn't talk about in this video, please feel free to email me at dsimmons@wscc.edu, as you can see up there on as I typed it in there. Thank you very much. And have a pleasant day.